Okay, thanks a lot, and thanks to the organizer for this nice invitation. So what I'm going to talk is, as Babu said, BSM physics using the supernova neutrino flux. This talk is based in a couple of works that we have done in collaboration. I have done in collaboration with André de Gouveia, Juber Perez, and Manibrat Dassem. So along this workshop, we heard many times about all the flavor oscillations that we have measured in many different experiments. Here we have a few examples. For instance, this is Kamla, that was Daya Bay, and this is the result from NOVA. And all of them point to the fact that neutrinos are massive particles. Okay, if this is true, it seems to be true. A new fundamental question appears, which is what is the origin of the neutrino masses, or how we can explain that neutrinos are massive particles. Well, we can consider a very generic mass model, like very general Lagrangian term for the mass of the neutrinos, and we can identify several different scenarios. For instance, if we consider that the Majorana mass term is zero, in that case, neutrinos will be exactly Dirac fermions. That means that in order just to explain the origin of the neutrino masses, we need to add into the standard model some right-handed terms, right-handed fields. But the mass for the right-handed fields and the left-handed one will be exactly the same. We can have another possibility, which is when the mass of the Majorana mass is different from zero, and in fact is quite large. People typically use this model just in order to explain the smallness of the neutrino masses, because the mass of the active neutrino will be suppressed by the scale, by the mass of the Majorana mass. So therefore, you can explain why the active or the mass of the neutrinos are so small. But there is a third possibility, that is the one that we are going to consider here along this talk. This is the case where the Majorana mass is different from zero, but it's actually very, very, very small. In that case, the mass of the active neutrinos will get two different contributions. One of them is the one coming from the Dirac mass, and the other one will be by the Majorana term. Okay, in this scenario, what we have is if we assume that, for instance, we add into the standard model just three additional right-handed terms, the mixing matrix that correlates the mass state with the flavor state is just given by this expression from here, where this U is just the PMNS matrix that we have in the electronic case. We have a UR, which is just coming from the diagonalization of the sterile sector. And also what we can identify is that each active neutrino can be written as a superposition of two massive states, where they are weighted by the lepton missing matrix, or essentially the PMNS matrix. So the idea of the scenario that I'm talking here is essentially that the active neutrinos can be written as a superposition of two states that are almost degenerate in mass. So that means that we are talking here about three pairs of almost degenerate massive state, and the difference in mass is just given by the product between the Dirac mass and the Majorana mass term. This small gap between the massive is going to introduce a oscillation, not in flavor in this case, but in this case will be between active and sterile neutrinos, and this is what is going to drive all the sensitivity that we are going to study here. Is there any bound on this scenario? Well, actually, yes, there are several bounds. In particular, if you consider all the experiments that we have in the Earth or outside the Earth, like for instance, the Sun. Actually, the Sun is one of the strongest bounds because it's very far away, and actually the energy for those neutrinos is very small. The bounds is of the order of 10 to the minus 12. That will be around here. The issue is that in the Sun, we don't produce the third massive state. We only produce mu1 and mu2. If you want to put a bound over the mu3, you need to go to atmospheric neutrinos. But the issue with atmospheric neutrinos, or the reason why the bound is smaller, is those neutrinos cover a smaller distance and they are more energetic. Therefore, the bound that we get from there is smaller. There are other scenarios that, although it has not been studied by the moment, can also drive us some sensitivity over this scenario. For instance, a high energy astrophysical neutrinos, like the one that IceCube observed. In that case, the range of values for the mass of the mass splitting that you can explore is very small. That goes from 10 to the minus 18 to 10 to the minus 12. That will be around here, no? Very high energy neutrinos, but the distance that they are covering are really, really large. But in this talk, I'm going to focus essentially on supernova neutrinos. They are not very far away, or we can consider that they are closer in distance than compared to the high energy neutrinos, but the energy for those flux is smaller. Therefore, the range of mass splitting that we can explain are essentially smaller. Okay, so what do we have in a supernova? Essentially, what we have in a supernova is a huge flux of electron neutrinos, anti-electron neutrinos, and mu x. Mu x is the sum of nu mu, anti-nu mu, nu tau, and anti-nu tau. This flux is the one that we observe here. This is just the distribution as a function of time. Well, this is just one of the prediction, one of the models for that. But along the talk, I'm not going to use any model for the prediction of the flux of this supernova. What I'm going to use is the time-integrated flux that has some energy dependence that is given just by this equation from here. This is coming just this is called typically an alpha fit, and essentially depends on a couple of parameters just to describe the energy dependence of the flux for each neutrino species. Essentially depends on the average energy for each species, this one, and also the alpha parameter that give us the width of the energy distribution. Here what we have is the flux of anti-electron neutrinos that we can, or the energy distribution of flux of anti-electron neutrinos that we can expect in the air. And essentially, this flux is just given by this equation from here. What we can see is that we will have two different contributions to the flux of anti-electron neutrinos. One is coming from the electron neutrinos that are created in the anti-electron neutrinos that are created in the supernova, and they arrive as anti-electron neutrinos to the air. The probability of this survival probability just is described by the MSW effect, and is given just by this term from here, which is just the coupling between U1 and E of the electron mixing matrix. And also we will have the second contribution coming from the nu x that are oscillated into nu e. But how is this energy distribution change if we consider a pseudo Dirac scenario? Well, the deviation in spectra is huge, as you can see here. And essentially what you have to account is for the active to sterile oscillation, or let's say in the other way, the active to active oscillation. That the equation for the oscillation probability is just given from here. And this is the deviation in spectra, or the deviation of the energy distribution that you get once you account for those oscillations. Now, another thing that you can see in this equation is that there are two different length scales that are important just in order to describe our problem. One of them is the oscillation length, that is the same that we have in all the oscillation experiments. It's just given by the energy divided by the mass splitting. The issue is that here, for the distance covered for the supernova, that typically is of the order of kiloparsec or tens of kiloparsec, in order just to have a coherent oscillation, the mass splitting that we need here is of the order of 10 to the minus 19, 10 to the minus 20. Okay? But there is another problem, is that due to this huge distance traveled by those neutrinos, the massive state, or the wave packet that form the interaction, the wave packet that make the sum of the neutrinos, if they propagate a long enough distance, they can at some point separate, and then the oscillation stops. That is what we call, or is given by the coherent distance. And the effect of this coherent distance is what is going to happen is it's going to kill the oscillation in the way that we observe here. At very far distance, we don't get any oscillation. Everything is done, and what we get is just the average of the oscillation probability. This coherent distance depends on the mass splitting for the neutrino, but also depends on sigma x. Sigma x essentially is the size of the wave packet of the neutrinos, and it depends on the production of the neutrino production mechanism. The value for this sigma x is of the order of 10 to the minus 13 meter, more or less, by the way. Okay. So since we are talking about supernova, we know that the flux of anti-electron neutrinos from the supernova 1987 was measured in, well, 1987. Actually, it was measured by 3 different experiments. Kamioka, IMB, and Baksan. And that was a type 2 supernova. The distance is estimated is of the order of 50 kiloparsec. The mass for this supernova is 20 solar masses. So the idea that we are going to use here is we are going to make an analysis of this data just in order to look for this pseudo Dirac scenario. In order just to do that, we have to define our likelihood. The fact that we have just a few number of events, we are not going to make beams in energy. What we are going to use is just an unbeam likelihood. Essentially, the idea of the unbeam likelihood is just a Poissonian likelihood where we assume that the size of the energy beam is small enough to have at least one, or at most, one event. This likelihood function has two contributions. One of them is the signal that is coming from, the prediction of the signal is just given by the convolution of the flux of the neutrinos function of the energy, the cross-section. All those experiments, those three experiments observed the anti-electron neutrinos, and the cross-section was inverse beta decay. You have to account for the detector efficiency and also the uncertainty in the reconstruction of the neutrino energy that you have also is given just by a Gaussian uncertainty. The second contribution is the background. Since we are using a time-integrated signal, we are going to consider all the background that can happen in those detectors in a time window or time windows of 30 seconds. Okay, and this is the result that we get after the after making analysis of each experiment, and also after a combined analysis of the three experiments. The first thing that we can see from here is that we get a sensitivity around the mass region that we expect, which is of the order of 10 to the minus 20, 10 to the minus 19. In the analysis, what we have done is we have considered that the normalization of the supernova, or the total flux of the supernova, is free. We have also considered that the average energy of nu E and nu E and nu X is completely free. We have considered that the size of the wave packet is fixed because it's just the production mechanism. And we have considered also that the alpha parameter is also fixed, although I am going to show you how is the impact of this parameter in the result that we get here. Another interesting result that we get is we get a preference for a mass which is different from zero. Why is where we are getting this preference for this region? Well, essentially because if you see the energy distribution of some of the events, there are some energy region where we don't get any event, and therefore it's better just to, if you include in your energy distribution, if you include an oscillation, it's better just to the field will really improve just because there are some energy region where you don't get any event. Also, for instance, in the case of IMB, when you once you include the oscillation, you get a wider prediction of the number of events in terms of the energy, and actually that makes you to favor a preference, but actually the preference is very small. Another interesting aspect is that we get the same sensitivity for very low masses. That will be the case where the neutrinos are not oscillating by the time that they approach the Earth, compared to the case where the neutrinos oscillate a lot, or that means that we cannot resolve for this range of masses the oscillation. Why we get the same sensitivity? Essentially because we are leaving in the analysis the normalization of the flux of the totals of the supernova. We are leaving as a free parameter. There is another aspect here, which is that we are able to explore with a delta chi square larger than 9 some region of the parameter space. And why we are getting that? Well, essentially, it's mainly Kamioka, and it's IMB, the one that drives this sensitivity. What is predicted for this range of masses is that the number of events for energies around 20 MeV, in the case of Kamioka, should be the same as energies of the order of 10 MeV. But also for the same mass, it is predicted that IMB for energies of the order of 40 MeV, they should not observe any event. And therefore are both experiments the one that put a strong constraint for this range of masses, and therefore they are able to prove mass splitting that are really, really small, actually of the order of 10 to the minus 20 electron volt square. Okay, but you can question why, but you have fixed the alpha parameter. How important is that? Well, actually, what we observed is that it's not very important. We get more or less the same result if we change by the alpha parameter by completely different values. Essentially, we get the minimum in the same region. We also get the same exclusion for very large and very low masses, and also the exclusion that we get around the same range of masses of the order of 10 to the minus 20 is of the same order, a delta chi square of larger than 9. Okay? But also another question could be, okay, fine, but if you add the pseudo-Dirac scenario, how is modified the prediction that you get, for instance, for the total flux of the supernova or the average species, average energy for each neutrino species? Well, it is modified, but actually there is not a very bad agreement in the sense that in the dashed line is what we get is the 90% confidence level just without a sterile pseudo-Dirac scenario, just in the standard case. And the color region is what we get once we add the pseudo-Dirac scenario and we make a profiling over this mass splitting. It's true that we get larger values, but around the 1-2 sigma region, there is a huge parameter space where they coincide. Okay, this is regarding the present status, but in the future, as we have heard many times along this workshop, there will be several experiments that they can put or they can measure the flux of the supernova neutrinos with a huge precision. So we question ourselves what will be the precision of those experiments in order to measure this pseudo-Dirac scenario. One of them that we have considered is Hyper-K. We have focused just in the main interaction channel, and for the case of Hyper-K will be inverse beta decay, the same as we get before. And here, we have considered a volume of the order of 118 kilotons. We have considered the same energy as the one that they have for solar neutrinos. And this is the event distribution that we get for 3 different values. As you can see, well, this is the number of events divided by 1000. This is the prediction for a supernova that is happening around 10 kiloparsecs, so it's far away. And as you can see, the precision that they can get is essentially huge. We have considered 3 benchmark scenarios. One is where the neutrinos are essentially Dirac particle. Another one, which the scenario is the neutrinos are totally in a decoherent state when they arrive to the Earth. And the other one is the best fit that we get from the previous analysis. And we get what we observe is like if that happens, Hyper-K could measure that with a huge precision. The same happens for Dune. Actually, we make also the same prediction. Here, the interaction channel is a little bit different. We heard before along this workshop that the main interaction channel will be the neutrino absorption in argon. We account for that. We include the energy resolution coming from Icarus, the previous some measurement that there are. And also what we get is the same. Dune can also look for these scenarios, and also they can place a strong bound. But we can search, okay, what is the range of parameter or the range of masses that can be covered in the pseudo-Dirac scenario considering Dune and Hyper-K. If a supernova at 10 kiloparsecs is happening. Well, this is the 95% confidence level that we get for both experiments. And the first thing that we see here is that both experiments can cover a huge range of mass parameters. The way in which you have to understand this plot is like we have drawn the sensitivity for each value of the sigma x. So we are not making an analysis or marginalizing over sigma x, essentially because sigma x is just given by the production of those neutrinos. So it does have nothing to talk about the pseudo-Dirac scenario. So, well, this is compared with the region that the analysis from Supernova, the region that we have excluded. And so therefore, if both experiments are able to measure a supernova and during the time that they are happening, they will be able to explore with a huge precision this region. It's very interesting to note that, for instance, for Hyper-K, they are able, in principle, to explore lower values of the mass. This is just because the detector is bigger, so therefore they can collect higher statistics. But in the case of Dune, because we have assumed that the energy resolution for them will be much better, they can explore larger values of the mass split. Essentially, the fastest oscillation can be better resolved in the case of Dune. Another interesting aspect is when the size of the wave packet gets very, very, very small. Essentially, all the oscillations are done, but the coherent effect depends also on the size of the mass splitting, and therefore all this region, the sensitivity is just driven by the coherent effect. Okay, so this is the sensitivity that we get with supernova, but okay, a core collapse supernova is a very rare process. It doesn't happen many times along our history, but it seems like in the future we will be able to collect, or we will be able to measure the BSM neutrinos. So neutrinos that are coming from the collection of all the core collapse supernova that has happened in the Earth. All the that has happened along the history. Now, the fact that those neutrinos has been traveling for a huge distance make us to think that the possibility, that they can explore values of the mass splitting that are smaller compared to the case of the supernova scenario. So, what is coming this sensitivity, or how we determine this sensitivity? Well, essentially, the DSMB is coming just by a convolution of the star formation rate, all the star that becomes a core collapse supernova, that is given just by this fraction given by here, and also the distribution of a star as a function of the redshift. That we use this particular parameterization here, and essentially you can see the distribution as a function of the redshift in this plot. What is interesting to note is that most of the stars are happening for a redshift around 1, more or less, and this is where most of the sensitivity is going to come from. Well, what is the spectra of the DSMB neutrinos that we can expect in our detector? Well, essentially that's the flux of neutrinos from the DSMB is coming just by the integral of this star formation rate, the energy distribution that we assume for we have taken for this Fermi Dirac, for the neutrinos from the DSMB, we have assumed a Fermi Dirac distribution, and also we have to account for the Hubble parameter that essentially is giving us, or depends on the dark matter distribution, and depends on the amount of the Hubble parameter, and also the amount of dark matter, and also matter in the, it's sensitive to the evolution of the universe. Well, how will we modify this the flux for this pseudo-Dirac scenario? Well, here you have two different plots. One of them, in the left one, we show you how get modified in the case of the mass splitting, in the case of different values for the mass splitting. As you can see, for very low masses, it's very difficult that we can resolve anything. But if we go to higher masses, for mass splitting of the order of 10 to the minus 25, the deviation that we get in energy from the DSMB is large enough just to think that we can maybe put a bound using for those values of the mass. It's also interesting that depends on the result depends on the size of the wave packet. If we consider wave packets that are large enough, there is no impact on the oscillation. But if the size of the wave packet is small enough, we cannot resolve the oscillation, but still we are going to have an effect coming from the recoherence. Okay, so the other thing is how it's possible that we measure the DSMB. We talked about this in the workshop. Essentially, the DSMB is an isotropic flux of neutrinos that are going to come with energies on the tens of MeV. It's going to be hard to be measured, but this has been produced, or has been described that, using gadolinium, you can reduce a lot the background that those neutrinos will, the background that will affect to those neutrinos. So essentially, if you use the background, you can get the neutron from the inverse beta decay interaction. You can, for instance, measure these neutrinos in an energy window that goes from tens MeV. Below that will be very hard because essentially the reactor neutron flux will dominate. And between tens of MeV and 30 MeV above that, you will have some background that is coming from essentially atmospheric neutrinos, and that's above those energy will be essentially very difficult because the flux will be totally dominated. Okay, this is the sensitivity that we get. The left plot, what we have is just the sensitivity for a couple of values of the size of the wave packet. Again, if the size, this size of the wave packet is not very well known, so you imagine. If the size of the wave packet is large enough, the sensitivity that we can get for an experiment like hyper K will be huge in this scenario. Again, for masses of the order of 10 to the minus 25, essentially all the sensitivity is coming from the oscillation that I show you. But if we go to values of the smaller, so that means that the neutrinos, when they arrive as an incoherent superposition of a state. We still are able to get some sensitivity over that, but essentially the sensitivity, as I was explaining before, is coming just from the coherent scenario. Here in the right plot, what we have is just the same scenario, just studying all the possible cases for the mass splitting for the size of this wave packet. And what is interesting is that we don't get any effect until we go to size of the order of 10 to the minus 14. Below that, the effect is essentially highly affected. That makes that we can exclude one region, more than 3 sigma, let's say. But for masses that are going to be of the order of 10 to the minus 26, well, 10 to the minus 25. Well, that's the conclusion. So if neutrinos are pseudo-Dirac particle, we can consider to explore this scenario using the supernova neutrino flux. We have made an analysis using the data that we have already. What we have seen is that there are some range of parameters that are excluded with a delta chi-square that is larger than 9. In the future, we will have better experiments that will be able to explore this scenario, and also we will be able to use new sources, like for instance the DSMB, if we are able to measure. And this DSMB essentially is a very good example where very small mass splitting can be explored. And that's it. Thank you.
Thank you very much. We have time for questions.
Thank you for a very nice talk. I was wondering, like in your DSMB uncertainty, do you only change the normalization, or do you also allow for the spectral shape to change?
No, we only we change just the normalization. Okay. We consider an uncertainty of the order of 40% in the normalization of the DSMB, and that's the only uncertainty that we include. Yes.
Okay, so like maybe it would be kind of useful to see how does that change if you also include the spectral information. Yeah. Because that
will be very useful. Yeah, definitely. That will be very useful. Just if we know how to modify this uncertainty in particular, because that will give us a better prediction about the sensitivity that we can have. Yes, absolutely agree. In particular, yes, you can draw. I mean, the sensitivity can be modified. The issue is that we need a way to modify this flux, and a consistent way. We cannot put whatever modification that we want, because that will be not actually fair. But yes, I agree with you. Yeah.
Thanks.
You have plots for Juno?
No, sorry.
So Juno will be sooner than Hyper-K, so it might be useful. Also, probably you should have plots for SKGD.
Yeah, we have some prediction for the SK. The issue is that it's not so good as Hyper-K, so I'm not showing you here, but because the volume is smaller. But actually, we made the prediction in the paper. We made the prediction for Super-K. Yes, the problem is the number of events that you expect.
Yeah, here is much too small number.
I mean, what is the prediction to measure the DSMB in Super-K? You expect to have order of 3 sigma sensitivity in 6-7 years. So at the end, the number of events you don't expect to be huge. So yeah.
So I have another question, and that is, did you do some kind of Toy Monte Carlo or other kind of calculation with delta chi-square of 9 means?
Sorry, say that again. Do you mean the analysis of the?
What delta chi-square of 9? What that means?
Yes.
How
no.
likely it is for a handful of events to produce a delta chi-square of 9 when there is no.
Yeah. No. We
if you doublet at all.
Yeah. Good point. No, we didn't make like a Feldman-Gaussian analysis or something like that about this. Delta chi-square. This is something that for sure will be needed to be done, just in order to account more for all the correlation that can also reduce the sensitivity. What we want to study is if there was sensitivity in the supernova 1987, we get something. We account for the systematic as we could, but we didn't make this analysis. That's true.
Other questions? Yeah.
Thank you. So I'm probably not thinking about this right, but You talk about decoherence with the size of the wave packet, but also your production, in the case of the SNB, the production region, so to speak, is highly uncertain, right? Because you have a diffuse.
Yeah,
flux.
but it's an isotropic flux.
Does that matter, or
no? Because what you expect from the DSMB is an isotropic flux. So what you are making is an integral over all the possible redshift. So it's not affected by the. There is no. I mean, what we are making in the DSMB is just an integral over all the possible directions that we have, as you can see here. So there is no. I mean, there is no flux coming from one particular direction. It's that we are integrating for all of them. Actually, we are integrating along all these spectra, even for redshift larger than this one.
So my question is even more stupid than that. It's like, if it's an oscillation, then it's L over E.
Yes.
So your L is.
The L
everything.
is given. No, the L is here. It's depends on the It's given by the set.
It's integrated over.
Yeah, it's integrated over the.
The wavelength is ridiculously long. Yeah, so there's kind of almost a.
So you don't have an oscillation, so to speak, right?
What do you do? But it's just that these things are coming from very far away.
Yeah.
And they're produced in a equal something region approximately.
Yeah.
So that effect is also have to be taken into account, but it is.
Yeah.
But somehow this wave packet size, if it is something to worry about, has a more significant effect if the wave packet is super tiny.
Yeah.
And we were kind of agnostic about what's the right size of the wave packet.
Mm-hmm.
Because that was the thing that I wrote.
Interesting. Yeah,
Actually-
I'll think about it. Thank you.
Yeah.
I don't know if it's related. In a few slides after this, you showed this plot. I was trying to understand the feature where the chi-squared flattens out.
Oh, this is because of the lack of statistics. I mean, the simulation that we did, but it will be like something like go up and.
No, I mean on the.
Oh, here.
No, left plot. But,
this one.
Yeah, the chi-square just becomes flat.
Yes.
And doesn't move it. Is it
It's
kind of
because-
like an oscillation? You just average out the effect.
Exactly. It's because the same that happened when you consider an oscillation that is quite fast. You lost all the sensitivity over the mass splitting. The only thing that you get is just the damp effect that you get. Essentially. But in this case, you also have to account for the fact that coherent mass also introduce an effect there and also modify that.
Okay, thanks.
Yeah.
Other questions? I want to ask one question. So the splitting mass splitting that you're interested in, 10 to the minus 20 electron volt square.
Yeah.
Do you have any kind of idea how it could be related to the actual mass itself? In other words, are there some theoretical idea which connects the delta m squared with the actual mass itself?
No, I don't have any prediction why there should be that mass splitting of that order. I don't have any prediction. Actually, yes.
Okay, it would be interesting to
see if
some theory connection to the needed mass splitting for sensitivity.
Okay.
Any other comments or questions? Well, if not, let's move on.
Yeah.